In this lesson, we will use the knowledge that you acquired in the last lesson in order to study your first operational amplifier circuit. Operational amplifiers are also known as op-amps. These are integrated circuits consisting of multiple semiconductors. There are many different designs made by different manufacturers, and each design has different characteristics which can be better for certain tasks. With operational amplifiers, it is possible to perform many different tasks, for example, adders, subtractors, integrators, and filters, to mention a few. The most common symbol for the op-amp is the one shown in the image. You can see that it looks very similar to the symbol of the amplifier we used in the previous lesson. It has a terminal for the positive voltage, a terminal for the negative voltage, and an output. Here you can see the basic model of the op-amp. It consists of a voltage sensor connected to the positive and negative terminals. Then the measured voltage is passed to a high gain stage that amplifies it. After it is amplified, the value is converted back to voltage and sent to the output pin. This behavior can be described by the following equation, which practically is the same as the one we used in the last lesson. Now let's try to build an amplifier with feedback, like the one in the last lesson, but now with electric components. In the diagram, we can observe that we have a voltage V1 connected to the positive input of the op-amp. The output is connected to a voltage divider formed by resistor RF and R1. The middle of the voltage divider is connected to the negative terminal. In this case, since the negative pin is connected to a voltage measurement device, the current that flows into the negative and positive pins is negligible and it does not affect the voltage divider. Let's get the formulas for this circuit. We start with the basic equation of the op-amp. Using the voltage divider formula, we can obtain the voltage at the negative pin. Then we replace that value into the initial equation, and after solving for the output voltage Vout, we obtain the following formula. The formula is given in terms of the resistor values, the amplifier gain, and the input voltage. As we learned in the previous lesson, interesting things happen when the gain of the amplifier is very high. If we take the formula and we calculate the limit when the amplifier gain tends to infinity, we can see that the formula is simplified. We obtain that the gain of the amplifier is given by the following formula. 1 plus the ratio of RF and R1. In this specific configuration, we cannot attenuate the signal, we can only amplify it. Operational amplifiers are designed to have a very large gain. Some of the amplifiers I use have a value around 200,000x of amplification. For practical purposes, we can assume that the gain is infinite, and that will allow us to use the simplified formulas when calculating the values of a circuit. Let's put numeric values and see the results. In the following simulation, resistors R1 and RF are 1 kilo ohm. Therefore, the gain of the amplifier is 2. In the plot, we can see the simulation results. We can observe that effectively the output is twice the input voltage. This op-amp model has a gain of 200,000x. We can see that with this gain, the result is very close to what we will get with an infinite gain op-amp. The formula for the gain of the non-inverting amplifier reveals two special cases. What happens if the value of RF is 0 ohms? In that case, the output of the amplifier is connected directly to the input, and we get that the gain of the amplifier is 1. The second case is when the resistor R1 is infinity. An infinite resistor is equivalent to not having a resistor, so we will completely remove it from the circuit. In that case, we end up with a gain of 1. Usually, an amplifier with gain 1 is built as shown in the diagram. The output is connected to the input. In this case, RF is 0 ohms and R1 is infinity because there is nothing connected. This circuit is known as the unity gain buffer or as voltage follower. It is an amplifier that just creates a copy of the input signal. Since this circuit does not amplify neither attenuates, so what's the utility? So let's see an example. Imagine that we need to create a circuit that given an input voltage V outputs the voltage V over 2 and V over 4. The naive way of doing it will be to design two voltage dividers as shown in the diagram. The first one is built with the resistors R1 and R2. Since they are the same value, the output will be half the input voltage. After that voltage divider, we connect a second one, formed by resistors R3 and R4, in order to reduce the voltage to the half. Therefore, we obtain a quarter of V. If you have been paying attention to the lessons, you may have already spotted the problem with this circuit. Let's simulate it to get the results. In the plot, you can see in blue the input voltage, orange is the voltage at the first voltage divider, and in green, the voltage of the second. You can see that the voltages do not match what we expect. Since the input is 4 volts, we want to get as output 2 volts and 1 volt, but both values are wrong. The problem lies in the fact that the second voltage divider affects the first one, since there is a current I2 flowing into the second voltage divider. In order to fix this circuit, we need to avoid any current flowing from one voltage divider to the other. One possible solution is to use voltage followers. As we mentioned before, the input current into the op-amp is so low that it can be ignored. We can use it to create a copy of the voltage without affecting the rest of the circuit. In this diagram, you can see two voltage followers. The first one creates a copy of the first voltage divider and provides it to the second. The second voltage follower makes a copy of V over 4 and provides that voltage to be used without affecting the behavior of this second voltage divider. In the plot, we can see the simulation results. These results are correct. For 4 volts, we get as output 2 volts and 1 volt. As you have seen in the previous exercise, when connecting circuits, the behavior of them can change. And if we are not careful, we may end up with strange behaviors. One way of breaking these dependencies is by using circuits like the voltage follower. But does that mean that we always have to use voltage followers when connecting subcircuits? Well, not necessarily. Let's analyze the following connected subcircuits to draw some conclusions. In the diagram, you can see a very simple subcircuit consisting of a voltage source and a resistor. The resistor represents the output resistance or impedance of the circuit. Real circuits always have an output impedance. This can be the result of imperfections or parasitic components or real components connected at the output. Similarly, subcircuits can have an input impedance. In this case, the impedance is modeled as a resistor at the input of this subcircuit. Let's imagine that we are measuring a voltage from a sensor called V1 and we want to send that signal to other subcircuit and receive it in a voltmeter VM1. Since two resistors are involved, the output impedance and the input impedance of the second subcircuit can affect the voltage that is measured. Let's calculate it. Since it is a voltage divider, we already know the formula. Let's imagine that both the output and input impedances are the same value. In that case, we know that the voltage measured will be the half of VM1, and that's not very good. What options do we have to make the voltage Vm equals to V1? The first one is to have a 0 ohm output impedance on subcircuit 1. In that case, the formula is simplified and effectively Vm1 is equal to V1. The second option is having an infinite input impedance on the subcircuit 2. In reality, it will be almost impossible to have an infinite input impedance or 0 output impedance. Therefore, a good enough solution will be to have an input impedance much larger than the output impedance. In that case, the measured voltage Vm1 will be approximately V1. In some circuits, the impedances are good and they can be connected without many problems. But in cases where the impedances are not good, we can use voltage followers to reduce the output impedance and also to increase the input impedance. To summarize this lesson, we learned the first op-amp circuit, which is the non-inverting amplifier. This circuit can be used to amplify a signal, but not to attenuate it. The gain is defined by the formula 1 plus the ratio of the resistors Rf and R1. We also learned the voltage follower, which can be used to create a copy of the voltage. This circuit has very high input impedance and low output impedance. That property is very useful when connecting multiple subcircuits.